I decided to call this module the Problems and Promises of NMR Spectroscopy because it's important for us to have a good understanding of all of the great advantages NMR spectroscopy has, but also many of the difficulties that NMR has compared to the other types of spectroscopy. And this particular section in particular focuses on quantum mechanics and could be subtitled Quantum Mechanics Giveth and Quantum Mechanics Taketh Away. There are gifts, there's a significant gift quantum mechanics gives to NMR spectroscopy that gives it characteristics that the other forms of spectroscopy don't have, but also quantum mechanics gives NMR a significant problem the other forms of spectroscopy don't have as well. In order to start seeing this, first take a quick look at this UV-Vis spectrum. And in particular, I want to focus on this one peak here, this fairly significant one in the ultraviolet. And a standard measure of width of these things is to simply look at the position of the peak on the left side and on the right side halfway up. And looking at this one carefully seems to indicate that the left side of this peak is approximately 260 nanometers and the right side approximately 240 nanometers. So it's approximately about 20 nanometer wavelength width to this thing. Now what I want to do is use some of the skills we've learned over the past several modules, including figuring out the frequencies associated with these wavelengths when we talked about NMR and how it relates to the other forms of spectroscopy. And in order to do that, I'm going to make use of our old friend, the speed of light equation, which remember is what relates wavelengths to frequencies. And I'm going to turn these wavelengths into frequencies. And one of the key things I'm going to need is to turn these numbers like 260 nanometers first into meters, because that's what the speed of light is given as. I should put that in there too, 3.0 times 10 to the 8th meters per second. So 260 nanometers, there are a billion nanometers in 1 meter. And if you simply do that calculation, 2.6 times 10 to the negative 7th meters. And if you take the speed of light equation and solve it for frequency, you get that, and then just plugging and chugging the numbers. 3 times 10 to the 8th meters per second, the speed of light, divided by the 2.6 times 10 to the negative 7th meters, gives me a value in reciprocal seconds in hertz, and that value is 1.25 times 10 to the 15th reciprocal seconds, or hertz. Now, if I repeated that calculation with the 240 nanometers, I would come out with 1.15 times 10 to the 15th hertz, or reciprocal seconds. It seems like the numbers are very close together, and indeed on this scale they are very close together, but realize what that means. If you subtract the two numbers, the difference is 1 times 10 to the 14th hertz, or reciprocal centimeters. Do you realize that means this one peak in a UV spectrum is over 100 trillion hertz wide? That is a wide peak, 100 trillion hertz wide. That is a characteristic of ultraviolet visible light spectroscopy. Now, I want to compare these kinds of numbers to what we see when we measure NMR spectra. So a little bit with a magic eraser, and let's take a look at those. Now take a look at this peak. This is the methyl singlet from methyl ethyl ketone, our reference standard that we've come to know and love so much over the time we've been in this course. Now, what I've done is I've taken that one peak and put it, just magnified it greatly, and applying the same kind of measure to peak width. I want to look at the frequency or the ppm value roughly halfway up on the right side and on the left side of this peak. And when I do that, the numbers approximately look like this. On this side, I have approximately 2.058 ppm to approximately 2.054 ppm. Now, ppm, while related to frequency, aren't exactly frequency. We've already talked about converting ppms into hertz and that chemical shift business. Going ahead and doing that, I'm going to take the 2.058 ppm. And on our particular instrument, remember, 1 ppm is 400 hertz on proton. And that's going to give me a value of 823.2 hertz. And if I repeat that with a 2.054 ppm value, I get 821.6 hertz. And the difference between those two numbers is 1.6 hertz. Look at that number for a moment. Compare that with what we saw with the ultraviolet absorption peak a moment ago. It was 100 trillion hertz wide. This NMR peak here is 1.6 hertz wide. Notice how much narrower that is. And realize one other significant thing. An entire proton spectrum that we've looked at, we've seen many of them now. The 0 to 12 ppm common range that we see. 12 ppm translates into 4,800 hertz. The entire width of an entire proton NMR spectrum is 4,800 hertz wide on our instrument. Do you realize that would fit inside one UV vis peak 1 billion times? Even a graphic that looks something like this does nothing to convey the difference between these two. A UV vis spectrum peak is enormously wide compared to anything we see in NMR. If NMR had the same peak widths, resolutions that UV vis has, do you realize we would lose our ability to measure any chemical shifts? We would lose our ability to measure any coupling patterns. We would not have any signals that we could integrate. All of our information, or almost every bit of it, would be gone. The only thing I could tell you was, yes, this sample does or doesn't have a hydrogen in it. Yes, this sample does or doesn't have a carbon in it. And that's it. Nice, but not nearly why we bother studying NMR. The takeaway message from this is realize one thing. NMR is an extraordinarily high resolution technique. Our peaks are extraordinarily narrow. We measure the frequencies in this technique extraordinarily well. Okay? They are well defined compared to any of the other forms of spectroscopy. UV vis here I'm using as my example, but IR would have something similar going on. Its peaks are enormously wide compared to NMR. Now, of course, we have to ask ourselves, well, why is that? And the root of it is in quantum mechanics and something called the Heisenberg Uncertainty Principle. Now, the Heisenberg Uncertainty Principle is a concept that many students have heard of. It's a fairly common thing to pop up in popular culture and so forth. Often people don't have a very good feel for what it means, but the phrase is quite familiar to folks. What it tells us is that basically any two related quantities, any two related measurements you might want to make cannot both be known with absolute precision at the same time. The most common example you hear from physics is position and momentum. For a particle, you can not know both its position and its momentum with equal precision. You either know where it is, but not much about where it's going, or you know where it's going, but not much about where it is at the moment. For us in spectroscopy, the two quantities that most directly affect us instead of position and momentum of a particle are energy, and the uncertainty or the fuzziness, if you will, in an energy measurement versus the time that it takes to actually not to necessarily carry out the measurement, but the time it takes for the transition between one state and another to occur. And the uncertainty principle says that these two multiplied together will have to be greater than or equal to Planck's constant. Notice they're on the same side of the equation, which basically implies energy and time are inversely related to each other. Said in words, it basically means the following. If the time of a process being studied by spectroscopy is very well defined, in other words, we know the time very well, we must therefore have a good deal of uncertainty in the energy of that transition, and therefore the frequency of that transition. Okay? So, stated simply, know time well, okay, uncertain energy, which means an uncertain frequency. Okay? And we see that in the visible region UV-Vis spectra value. UV-Vis looks at electrons moving between various energy levels. Those processes are fast. They are on the picosecond. They're on the femtosecond time scale. Electrons jump between energy levels extraordinarily fast. That means the time that it takes for them to go is very well known. There is no, well, it might go in the next little while or not. We know exactly, how long that process is going to take. We know exactly, within what time frame it's going to happen. It's going to happen in the next picosecond, in the next billionth, in the next trillionth of a second. Time in UV-Vis spectroscopy, since it's such a high energy type of spectroscopy, is very well known. If time is very well known, energy is therefore uncertain. And if the energy is uncertain, the frequency of that transition is uncertain. And that shows up in this very wide peak. The frequency of that transition is known to within, plus or minus a trillion. Okay? That is what we mean by fuzziness or uncertainty in energy and frequency. NMR spectroscopy, on the other hand, is a very low energy. It's the lowest energy spectroscopic technique. We've already talked about that one. Given that it's such a low energy technique, it is also a very slow technique. I know that this proton, for example, is going to change its spin state, and it'll change, let's say, in the next 1 second of time. Now, 1 second is pretty quick on the human scale, but realize that is trillions of a picosecond. In other words, NMR is incredibly slow compared to UV-Vis. The time is very uncertain and fuzzy. It could happen anytime within this next 1 second. That, on the grand scheme of things, is actually a very slow process. So in NMR, it is the time that transition occurs. That is what is fuzzy or not well determined. So if you don't know this one very well, you do know the energy. When that transition finally does decide to occur in the next 1 second, I will know its energy, and therefore I will know its frequency very well. Okay? And so uncertain time leads to well-defined energy, which means, certain, quote unquote, frequency. In other words, a frequency measured to within plus or minus 1 hertz. Okay? very well defined frequency for NMR. So this is UV, this is NMR. And this is Heisenberg's gift to NMR spectroscopy. The process is very low energy, very slow. That means time when these processes will occur is very uncertain, so to speak. That, in other words, our energies therefore are very well defined, our frequencies are very well defined, our spectra are very high resolution. So NMR is a high resolution spectroscopy. Compared to the others. That is what allows us to measure very subtle chemical shift differences. That is what allows us to see different peaks separated so much that we can integrate them successfully. That is what allows us to see the very lovely coupling patterns that the next module will dive into deeply. That is what is responsible for the avalanche of information that NMR gives us. It is rooted deep in quantum mechanics, and it's quantum mechanics' gift to NMR.